Okay. So hi everybody. I think it's, I mean, without knowing, it's super cool that I'm after Annie because I did exactly like the opposite as you did. Uh, so I try to use a cellular automaton to do a bottom-up model of how a cell colony grows. So the basic idea is that in many contexts, people have like seen how bacteria colonies grow, and based on the nutrient level that is there in the environment, there are different shapes that the colonies can take. And here is an example, like 4 examples of different morphological shapes that the colonies can take, and they can, I mean, in some cases they are very compact. In some cases, as in the B picture, they are really branched. And what impacts this is, as I said, the nutrient level, and on a lower scale, also other parameters like pH, like other environment variables. Um, and about in particular the branching colonies, there are two length scales involved. The first one is the bacterial cell scale, which is of the order of the micron, and the other is the length, which is measured of the branches of the colony, which is of the order usually of 10 to the minus 4 meters. Which is, I mean, 2 order of magnitude difference, but not too different. And so it has been proposed that cellular automata could be a good way to try to model this system, because you can, I mean, the length scale of your cell is more or less the same as the one of the branches. And so to see the dynamics at the cell level, it would be appropriate to use a cellular automaton. In particular, what I implemented is a cellular automaton where each element is one bacterial cell. And to take into account the nutrient diffusion, I only consider nutrient and not other parameters, so no pH, no. So it's a very simple model. And to deal with that, I use a reaction diffusion equation, and I couple these with the cellular automaton to when I update the state. So in principle, one could avoid using the cellular automaton and use reaction diffusion also for the cells. But to see really the individual cell movement, I thought it would be, I mean, cool to see this hybrid approach. And actually, I mean, people did it already for like the reaction diffusion equations for also pH, nutrients, and cells in the reference tree. Yes, so what I do in practice, I have a 2D cellular automaton, which is stochastic. So the update rules include I extract some random numbers when I have to update the system, and I will show later how. And I couple it with the concentration field, which I can see. I set a lattice constant, which I mean I need because I have to solve the equation for the concentration field. The neighborhood I take into account is von Neumann, and I set periodic boundary conditions on the four sides. And the states I have in my system are three, either empty, active, or inactive. And the transitions that I can have are first the so-called inactivation. So an active cell can become inactive if the nutrient concentration at that place is below a certain threshold. And this, like the physical interpretation, is that if the cell has not enough food to survive, then it becomes inactive. The second reaction I have is the growth. So an empty cell can become active. And the idea behind this is that an active cell can duplicate, can like divide. And here is where stochasticity comes into play, because when a cell divides, it basically searches around the neighbors. And if there is an empty space, it selects randomly where to put its daughter cell. And in the case that all neighbors are occupied, then the cell division does not take place. And I assume the cell remains active, and it basically consumes the nutrient without giving birth to a child. And the process of getting inactivated is not recoverable. So once you get inactivated, you just stay as you are. And another thing that I added to take into account the fact that like bacteria do not really all divide at the same time. I coupled the cellular automaton with another matrix which encodes a maturation age. And so as cell can divide only if it reaches its maturation age. If not, it does not divide. I took a normal distribution for that with the standard deviation, which is half of the mean. And after division, this age is reset, so the cell has to maturate again in order to divide. And actually, this is key for seeing the dynamics that I will show later, like the branching pattern. And as last thing, the nutrient field. So as I said, I'm coupling the cellular automaton with a field which I call C for the nutrient concentration, and it evolves according to this equation. There is a diffusion with diffusion coefficient D, and there's the nutrient consumption, and I assume K is constant and is equal for all active cells, and it tells us how much nutrient is consumed. N is yet another matrix where I encode the number of active cells. And so this N is 1 only if at position X the cell is active. Otherwise it's 0. So there's no, I mean, if there are no active cells, the nutrient simply diffuses. And then to solve this, I use Dirichlet at the boundaries, and I take fixed values at the boundary. And this, like, physically would mean that I have a constant supply of food from the boundaries of the system. And yeah, in practice, I just discretize the space and time derivatives, and I just update at each time step this field and accordingly update the cellular automaton. Yes, I initialize with uniform concentration across my grid, and here I show the grid, and a small central circular colony with a small radius, and black are empty cells, gray are active cells, and white, which are not present at the beginning, are cells that have become inactive. The first thing I did, so as I said, what is important is to take this concentration threshold, and because if concentration falls below this threshold, then cells become inactive. So the first thing I took it as a constant, like the same all across the grid. And here are the patterns that come out of this. So there are two different regimes. The first one, when the consumption rate of the nutrient is very high, and we get this front of active cells that sort of expands, and there's a border of inactive ones, and that in the end everything becomes inactive. And in the second regimes, we have a low consumption of the nutrient, and we get this branching pattern. Again, the active cells that are in the middle, and the branches that go towards the sides. And I was wondering, I mean, what would change, and if so, I mean, would anything change, and if so, what, if we change the threshold for the nutrient consumption? And there are two ways that I tried to change this threshold. So the first one is I simply set a random matrix that will tell me what's the threshold. The second one is to add a gradient. So I'm basically having a spatial gradient that tells me what's the threshold. And this, I mean, the biophysical interpretation would be that different cells could have different fitnesses or different resource consumption, and that could be captured by changing the threshold in this way. What changes if I add a random thresholding? Again, I have these two parameter ranges. For high consumption, actually everything is random, so there is not anymore the front of active cells. But interestingly, if we have a low consumption rate of the nutrient, still there are some branching patterns that remain, even if not as precise as they were before. And then if I add the gradient, again, in the regime of low nutrient consumption, we see that the branches are not so affected. So they're still not precise as the first picture showed, but still these branches form. And in the case in which the consumption rate is high, there's this sort of symmetric pattern, which I don't know. Every time it came out, and yeah, it sort of divides where at half of the gradient, and yeah, and yeah, to Sum up what I did, I just implemented this hybrid cellular automaton model coupled with a reaction diffusion equation to describe the growth of a colony. And I saw how the colony shape changes if I change the consumption of the nutrient and the thresholding for becoming inactive. And the case in which there is a low nutrient consumption is very robust against changing this thresholding. And there are many other possible extensions. So one could think of having different matrices of this thresholding function, but maybe, the ones that I took had like a physically sound reason behind them. Maybe, other choices may not have this physical interpretation. And one could also think of, instead of having the simple reaction diffusion equation with only a diffusion and the nutrient consumption at velocity term, so a flow of the nutrient, and see how this also impacts the growth of the colony. And then, of course, compared to real data, if there are many people in biology studying that, so it would be cool to see, how it compares to them.
So you have this constraint that two bacteria can't be in the same pixel, right?
Yes.
So how do you process the pixels when you want to decide who reproduces and where it goes? Because it depends on the order. Like if you start from left to right, maybe you will have some.
Yeah, I start from like top left, and I go like process the lines, and I basically what I do is I make a copy of my grid, and I, based on what I had in the older version of the cellular automaton, I see where is the empty space, and then I place
Okay.
like the new bacterium, and
I see.
I didn't try out other things.
So
Honestly.
I think I had kind of the same question, is that when you explain cell division,
Yes.
so you said that the parent chooses an empty space around it for
Yes.
the child, right?
Yes.
So so this kind of breaks the CA assumption, right? Because each cell is not responsible for its own revolution.
Yes.
Like the child does not choose to appear somewhere, right? It's the parent that chooses to place a child. And so I think the question from Esan was, if there are two parents that want to place a child in the same position.
Yes, random.
Yeah.
I pick random which one will go.
Okay, I see.
Yeah.
Okay. That's fine. I had a question on the patterns that you see. So I don't really understand at a high level, why do the inactivated cells appear as a boundary? So what is the high level explanation of that? Do you have?
That I don't have any idea, and that was
Okay.
Also counterintuitive to me, because I would have expected the opposite.
Yeah.
So I don't know. Either there is like somewhere a bug in the code that I have, because I would have expected the same, like to have inactive in the center.
In the center and growing at the
yes.
boundary. Yeah.
And I don't know whether it has to deal with the concentration, because of course then this is connected to the how I substitution for the concentration. Yeah. But I tried to look into that, but I didn't really find an answer.
That's fine. So I was wondering because
one reason might be that active ones can be inactive, but inactive ones can't be active. So once you're surrounded with inactive, you have no choice to either be inactive or remain neutral.
But the inactivity arrives when you have not enough nutrient, right? So it seems that in the middle there were cells for longer, so there should be less nutrient than in the border, right? Something like that. But okay, I was just wondering. Other questions? Otherwise, I had another.
What is the starting nutrient concentration?
It's one everywhere, like constant everywhere.
And there's no flux of nutrient, just from the boundaries.
Yes.
Okay. I was wondering, did you try only the initial condition, which is a point, or did you try kind of a line as well?
Try
okay.
Other things.
I think that would be nice to see what happens, what patterns you get with the line.
Yeah, but like I because I thought of that, and then I was like, it was weird for the boundaries, because if you think about like a line at the bottom, then you have to impose that you cannot go at the top, because then
right.
It's sort of weird.
Yeah,
so
I see.
I was a little bit
okay, I see.
confused,
I see. Yeah, and one thing I was wondering, so when the cell kind of looks at the nutrients,
Yes.
does it have a radius where it can eat nutrients, or
It's only at its place.
at its place? So you take like the average of the nutrient, because the nutrient is continuous, or it's discretized on the same scale as the
Discretized
seed.
on the same scale. I actually,
Okay.
yeah.
I see. And the last thing, I guess, was do you also have any videos to see how the growth happens?
I don't have the videos
Okay.
because I couldn't put them here. And
No,
I
that's
didn't
fine.
even-
Yeah.
sorry.
Okay. But you could see kind of the evolution
Yes,
of
that
the
it
growth, or you had
spreads.
okay.
Yes.
Okay. And okay.